Alright gang, here we go. This is Chem 2 Unit 6. We're talking today about calorimetry. Alright, so last video we talked all about this new idea, this new thermodynamic quantity called enthalpy. Okay, and we talked about how, remember anytime we talk about thermodynamics, really we've got our system and then our surroundings, right? And for the most part, finding exact thermodynamic values of what is in our system is not really possible. It is, some of them are possible, but a lot of times it's just too hard to do, and really it doesn't tell us much anything useful. So really what we care about is what's being transferred across the boundary of our system. Okay, and remember for our specific class, we say that anything that's leaving our system has a negative sign, and anything that's coming into our system has a positive sign. Okay, so that's kind of what we're running with for our idea here. Okay, and so we talked about enthalpy, and we can find total enthalpies. We can't really find total enthalpies. It's really hard. So we are going to find. So we really care about, well, is enthalpy leaving or coming into our system? Okay, and we talked about how our delta H, we can find our delta H just by taking the sum of all the enthalpies of the products, okay, minus the sum of all the enthalpies of the reactants. Okay, all right, and this is a little bit different than what we notation than what we did in the last video, but still, it's just products minus reactants. Now the problem is that for a lot of times we can't just measure the exact enthalpy. Okay. But what we can do is we can use what's called calorimetry, okay, in order to find the delta H of our system, okay. And really, when we're doing this, really what we're finding is the heat flow, okay. And so this is, and really heat is flow, so this is kind of a double, means kind of the same thing. This is, and remember, so this is going to be our Q value, okay. Anyway, so this is kind of a picture of like a very basic calorimeter. Okay, kind of close to what we'll use in class. We've got 2 styrofoam cups and then a solution. Okay, and we've got something to stir it, and then the thermometer measure the temperature change. All right, and so essentially what we do is we just mix everything together and read how much the temperature goes up. Okay, it's pretty easy. Okay, and so by doing that, what we can assume is all the heat that our reaction either gave off or lost goes directly into the solution or the water, whatever it is that's absorbing the energy. Okay, and now the reason this is important is because we can use this idea in order to find this new value, okay, called the heat capacity. Now everything has a different heat capacity. Okay, it's an intensive property. Sorry, an intensive property. So that means we can use it to identify an unknown. Okay, so the amount of energy required, the amount of energy required to raise the temperature of a substance by 1 Kelvin or 1 degree Celsius is its heat capacity. Now, remember, this is really handy, this idea of 1 Kelvin or 1 degree Celsius. Remember, because the difference between Celsius and Kelvin is just adding a number, you know that that 1 degree or 1 Kelvin, the change in 1 unit of in either of those scales is an equivalent amount of energy. Okay, so anyway, so we can really, they're all given in Kelvin, but when we're talking about change in temperature, we can just use the Celsius temperature units just right away. Okay, anyway, so the amount of energy required to raise the temperature of a substance by 1 Kelvin is its heat capacity. Okay, so this is defined how much it takes to raise that substance 1 degree. Okay, if your substance is exactly 1 gram, it has a special name called the specific heat. Okay. All right, so down here we've got a whole bunch of specific heats. All right, so nitrogen here, it takes 1.04 gram or 1.04 joules to raise 1 gram 1 Kelvin. Okay, and so mercury takes 0.14 joules per gram Kelvin. Okay, and you can see these molecular compounds over here. Like water takes a lot of energy comparatively to raise it 1 degree, right? So you have to add 4.18 joules for every gram. And for every degree you want to move up. Okay, now so if these are all specific heats, and then we can also have molar heat capacity where our moles are instead of it being in joules per gram Kelvin, it's in joules per mole Kelvin. All right, and you can you see both things tabulated. All right, and so this is essentially what this is meaning here, is that if we had 1 gram of water that's liquid water and we wanted to raise it 1 degree, so we're going from 14.5 to 15.5 degrees, we would have to add exactly 4.184 joules to raise that 1 gram 1 degree. Okay, pretty simple. All right. Let's do a practice problem or two. All right, we'll skip number 1. Number 2 says large beds of rock are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules per gram Kelvin. Calculate the quantity of heat absorbed by 50 kilograms of rocks if their temperature increases by 12 degrees Celsius. All right, so we need to find the quantity of heat absorbed. Now, you guys are a lot of you will probably be really good at this, because essentially what we're doing is we're just going to be playing with units. All right, and since we had lots of practice with this back when we did stoichiometry, this stuff should be pretty easy. So we have 0.82 joules per 1 gram Kelvin. Okay, we want the heat absorbed. Okay, so that means and heat is in joules. So we just need to get the joules by itself, which means if we can multiply by grams and the temperature, we'll be left with just joules, right? So we'll multiply by grams. So we have 50, and this is in grams, this is in kilograms. So this would be 50,000 grams. All right, and then we need the kelvins to go away. And so the kelvins increase, right, would be 12, okay, because those are equivalent to one another. So our 12 kelvins would cancel. So our grams cancel with grams, kelvins cancel with Kelvin. We take all that, so we take 0.82 times 50,000 times 12, and we end up with 492,000 is what I got. So we want 2 sig figs on this, so it would be 4.9 times 10 to the 5th, and it's heat, so our units would be in joules. Cool. So that's the answer to A. And it says, what temperature change would these rocks undergo if they emitted 450 kilojoules of heat? Okay. So if you look at this setup right here, okay, I want you to look at what we've set up here. So if we're just gonna, I'm gonna take this idea and I'm just gonna rewrite this information just as what they were. So this was the heat capacity, or the specific heat. So we'll call that CP. That's if you see CP, really mean this heat capacity. The C comes, I'm pretty sure, from the idea of using calories was the original unit for heat that were used in chemistry for a long time. So anyway, so heat capacity, all right, and then this was the mass, all right, so heat capacity times mass, and this was the change in temperature. So that was our delta T, and that was equal to our heat evolved, okay, all right, so and you could rearrange this equation if you wanted to for funsies. We could say our Q is equal to mCp delta T. Yeah, so I like to call this the MCAT equation, because you got mass times C, and then the delta symbol looks like an A. So you got MCAT, Q equals MCAT. So this equation right here is a really important calorimetry equation that we're going to refer to a couple of times here. And we just derived it all on our own because we're awesome. Okay, so but let's use it here. So what temperature change would these rocks undergo if they emitted 450 kilojoules of heat? Well, we want temperature change, so that's our delta T. So let's rearrange this equation here, solving for delta T. So our delta T, so we'd have to divide Q by mass and heat capacity. All right, so that means Q divided by our mass times our CP. All right, so our heat evolved was 450,000, because that's what they tell us right here, 450, 1, 2, 3. And I know I need to convert it into joules because my heat capacity is in joules. All right, so joules, and then our mass was the same mass. So that was our 50, 1, 2, 3 grams. All right, and then our heat capacity of the rocks was 0.82 joules, so 0.82 joules per gram Kelvin. And if you're savvy with your units, you can see that these joules will cancel, these grams will cancel, and you'll be left with just kelvins, and that's exactly what we need for our temperature change. So we'll take 450,000, oops, we forgot an important part. All right, we'll hit that in just a second, divided by 50, 1, 2, 3, times 0.82, all right, and we get 10.97 or 10.98, okay? But let's think about this for a second, all right? it says that they emit 450 kilojoules of heat. So that means because it's losing that heat, that means that's going to be a negative sign. So we have a negative 450,000. That's our Q value. So this is going to be a negative. Then we have to think about sig figs here. This guy's got 2 sig figs. So our answer becomes negative 11 degrees Celsius. So if our rocks emitted 450,000 joules, 450,000 joules, the rock's temperature would go down by 11 degrees. Okay. Now, constant pressure calorimetry, this is the kind of calorimetry that we do a lot of times in class, right? Because we just do things in atmospheric pressure, just in the laboratory, so we can assume that our pressure is constant, all right? So, so this makes it easy because once we do it in this simple calorimeter, if we find the heat change, we can just assume that's the enthalpy. Pretty nice, okay? So 99% of the time, we're just going to use water as our thing. So this is going to be what we'll use for our heat, specific heat when we're running aqueous solutions. Okay, and then so essentially what we can do is we can assume that our reaction is going to lose heat, right? Some reaction or some heat. It might gain heat, but it doesn't really matter. We can assume that the heat of the reaction is equal but opposite to the heat gained or lost by the solution. So if we can measure the temperature change of the solution, okay, we know, and we can calculate the heat gained or lost by the solution, we know that that is equal but opposite to the heat gained or lost by the reaction. And because it's constant pressure, we also know that this is equivalent to our delta H. Pretty slick. And notice that we have our MCAT equation. They put the C and the M opposite each other. So really they'd be like this. This would be a cool kid do. This is how the cool kids do it. All right. So anyway, so C times M times delta T. All right. Now we also have these other guys called bomb calorimeters, okay? And bomb calorimeters are sealed containers so that the volume, so that the pressure has to go up, okay? They keep the volume constant, all right? So because the volume's constant, they'll blow up, and it does some fun things. So essentially what we have is we have our reaction chamber, okay, or the bomb itself. So this is whatever we're blowing up, and you actually use electron probes to actually give it that ignition, okay? And then you measure the temperature change of the water outside of the bomb, okay? And so, and you can use this idea here, and then because of the way it's set up and because it's all sealed in here and it's a closed system, you can assume here that the Q of the reaction, okay, is just equal to the negative heat capacity of the calorimeter times the temperature change of the water. Okay, so we can use this anytime we're using a bomb calorimeter. All right, it makes it super easy, so take note of this one as well. All right. Now, one thing to keep in mind is that because the volume in the bomb calorimeter is constant, the pressure is actually increasing. So when we're making this measurement, really what we're calculating, we're not finding the enthalpy, okay? We're actually finding the internal energy. But really, for most of the time, like, those two things are essentially the same thing, so we don't really have to worry about it. And that's because in a bomb calorimeter, remember our internal energy, okay, our internal energy is equal to the Q plus the W, okay? And the W, remember, is pressure volume work. So pressure times change in volume, but because the change in volume is 0, essentially this is 0. Okay, our work is 0, so delta E equals Q, okay? And so anyway, so you can just kind of assume that your internal energy and your enthalpy are pretty much the same thing, all right? So let's do a couple practice problems here. Come on, you can do it. All right, here we go. The combustion of exactly 1 gram of benzoic acid in a bomb calorimeter releases 26.38 kilojoules of heat if the combustion of 0.550 grams of benzoic acid causes the temperature of the calorimeter to increase from 22.01 to 24.27 degrees Celsius. Calculate the heat capacity of the calorimeter. All right, so it's a bomb calorimeter, so that means we can use our new formula we just got. So our new formula was this guy back here, right? Q equals negative C delta T, okay? Okay, so our Q equals negative C calorimeter times the change in temperature, all right? So we can rearrange to solve for the calorimeter. So heat capacity of the calorimeter is equal to the negative Q divided by our change in temperature. Okay, now here's the tricky part. We have to find that Q, right? So we know that 1 gram of benzoic acid, okay, usually it will release 26.38 kilojoules of heat, all right? But we only reacted 0.550 grams of benzoic acid. So we'll multiply this heat by 0.550, and then that'll give us the amount of heat that was released when that much benzoic acid was reacted. All right, so it's negative, and we'll take 0.550 times our 26.38. Okay. Now, if we think about that 26.38 value, okay, it releases that heat, right? That's what's released, so this would be a negative value because it's exothermic, right? Now we divide that by our change in temperature. Okay, temperature change is always final minus initial. Okay, so it would be 24.27 minus 22.01. All right, so that means our heat capacity of our solution, okay, so we take our negative 0.550 times negative 26.38 divided by 24.27 minus 22.01. Okay, and we get 6.42 kilojoules per degree Celsius. So that's the heat capacity of our calorimeter. All right. All right, so now this guy says a 0.5865 gram sample of lactic acid reacts with oxygen in a calorimeter whose heat capacity is 4.812 kilojoules per degree Celsius. The temperature increases from 23.10 to 24.95 degrees Celsius. Calculate the heat of combustion of lactic acid per gram and per mole. Okay, so that means we just need to find the heat. Well, this is easy. Okay, we know that our Q, okay, is equal to, okay, negative 4.812, so it would be, so negative C cal times our change in temperature, right? So we'll take our, so it would be negative 4.182 times our change in temperature, so we our final minus our initial, so that's 24.95 minus 23.10, so that's a difference of 1.85 degrees Celsius. All right, so that'll just give us our energy release. So we take those two values, we take negative 4.182 times 1.85, okay, and we get 812, not 182, negative, sorry, 4.812. Yeah, you guys are probably yelling at your screens. Why did you flip those numbers? All right, here we go. So those two flipped. 812. There you go. 812 times 1.85. There you go. So we get negative 8.9022 kilojoules. So this is how many kilojoules this many grams of lactic acid evolved. Okay, but we don't care about how many grams or how much this amount. We want it per gram. So we're going to divide this by the amount of grams, and then that'll get us per gram. So we're going to divide that by our 0.5865. All right, grams. And this will give us kilojoules per gram. So we're just going to divide that by 0.5865. We get negative 15. 4 sig figs, negative 15.18 kilojoules per gram. Okay, so that's the answer to part A. Now in order to get it to part B, okay, that says per mole, so all we have to do is convert our grams to moles. Well, that means we have to find the molar mass of this guy. So lactic acid has 6 hydrogens, 3 carbons, and 3 oxygens. Okay, add those guys up. So 6 times 1.01 plus 3 times 12.01 plus 3 times 16.00. Okay, so 6.06 plus 3 times 12.01 plus 3 times 16, get 90.09. So that's the molar mass of lactic acid. All right, so then we're just going to use this value. I'm going to do it up here just so it doesn't get in the way of anything else. All right, so we had the negative 15.18 kilojoules per gram. Okay, we're going to convert that to kilojoules per mole. So we draw our line. We got grams. We put moles in the bottom. Put 1 for the moles. Our molar mass here was the 90.09. Okay, so we just take that times our 15.18. And we get, I went to 4 sig figs, so we get negative 1,368 kilojoules per mole. So that's the answer to part B. Okay, pretty easy stuff, not too hard, just more of the same. All right, so go ahead and do your practice problems, have lots of fun. Let me know if you have any questions, and I'll see you on the flip side.